Well, thank you everyone who came for the third day of NEARCON. I hope you all energized and did not drink too much yesterday. So I want to welcome Jordi here. Jordi is a co-founder of Polygon. He's a true OG of kind of Web3 and Ethereum space. And it's been kind of, on Wednesday we announced partnership with Polygon, working on ZK Wasm together. And Jordi is one of the brains behind kind of the push for zero knowledge at Polygon. And I wanted to sit down here, kind of very grateful for Jordi to come and discuss why zero knowledge technology is so important, how we got here, and what's coming next. But first, want to give word to Jordi to introduce himself and also tell us more how you got into zero knowledge, why it excites you.
Well, I'm an engineer. I'm an engineer since I'm 12 years old. That's my heart, where it is. I start working in the crypto space in 2015, so that's a little bit long time ago. And it was very early, maybe after 1-2 years, and understanding that the technology that actually I was trying to use this technology in real applications, and I realized that this technology doesn't scale. I mean, it scales if you centralize, but if you really want to decentralize, it doesn't scale very well. So that was my obsession at that point. I mean, at that point was time of state channels and very complex things that they didn't work. And at the same time, I was very excited about the zero knowledge, especially for the privacy stuff. So I started to study a lot here. I drink a lot from the Zcash people. I think that all the zero knowledge comes from them. We have a lot of them. A lot of thanks to that network by the time. And I built a couple of, I was building NEARCON, which is a language for creating zero knowledge circuits, and Snark.js, which is a prover that works very good in the browser. Right now is one of the most used tools in the space on that. And from there, we realized that this was very important also for scalability, because zero knowledge is not only about privacy, it's mainly about the scalability. Actually, scalability is the application that makes zero knowledge grow that much. People care less about privacy, unfortunately. And
Sadly.
Yeah, sadly, yeah. And from there, we created the first roll-up, the only payments roll-up that was called Hermes. And after we launched Hermes, we were start working in the Holy Grail that was, in this case, was a scaling Ethereum, scaling the EVM. So the idea was to prove an Ethereum transaction, in this case, that executes thing. This was a little bit of Holy Grail 2 years ago, because, even myself, I couldn't believe that this could be possible.
Yeah, it was hard to believe it will work because of complexity. So
yeah, so at that time, we remember we spent a couple of months with Barry Whitehat from the Ethereum Foundation, working together, trying to, it's impossible, but let's try it. Let's try to see what are the points and how we would do each of the pieces. And we're solving all the pieces, and at some point says, looks like more or less all the pieces are there. Some of them very complex way to do it, but it's possible. So from there, we start working hard. It was the work of 2 years. At that point, we joined forces with Polygon. We merged Polygon. Here was very important. We get all the funding and we could grow the team and actually put resources on that. And 2 years later, we were launching in mainnet the Polygon zkVM, and has been a long journey. We learned a lot, but I think this is an important milestone, not only for Polygon or for Ethereum, also for the full blockchain ecosystem, because actually we see that it's perfectly scalable. So scaling blockchains is definitively possible, and this is the way to go. This is the clear way to go.
So maybe for those who are not very familiar with how zero knowledge works, as well as how it actually transforms provable computing and applied to blockchain, maybe you can describe kind of in basic model how that works.
Yeah, zero knowledge is mainly is what we call the best way to understand, because there is a privacy part, but the best way to understand is what we call the provable computation. So here is the idea how it works. Imagine that I have a program, any deterministic program. This can be verify a set of transactions, but can be anything. I mean, any training
Yeah,
AI,
machine learning
whatever.
model, yeah, anything. Yeah.
Anything. Imagine that a program that takes 1 week to compute that. Okay, so have an input, you know that the program will uniquely generate an output because it's a deterministic program, and I give you the result to you. So you know the program, you know the program, and you have the result. And you want to verify, okay, you have the result, but are you sure that this result is correct? Well, the obvious way is, okay, you can verify that. I mean, you just take the same computer, the Mac supercomputer, you run the program again, stay for a week, and then you see that the result is the same. Okay, the computation is valid. Okay, but there is a better way to do that. And the better way is, okay, I have the program. Of course, I need to spend 1 week running the program, but besides doing the computation, I also generate computation proof, a ZK proof. Okay, so it's a very small cryptographic, like a kind of a signature, okay, as a cryptographic part. And then I give you the result. I give you the signature or this proof, this computational proof. And the cool thing is that you don't need to run the program again. You can verify that the computation is valid in very few milliseconds. And the cool thing is that no matter how long is this program, no matter how big, it can be 1 week of computation, 10 years of computation, can be the computation of a full blockchain. I mean, it can be whatever computation you want, that the verification, it takes very few milliseconds just to verify. And this thing that's quite new, I mean, this succinct part, this zero knowledge, the succinct computation part, this was until 2010 or so, was not even possible. So the research level was at level. But this is what allows blockchains to scale. Because what's the big limitation of the current blockchains, of current layer ones? Is that, I mean, the consensus is expensive. And if you want to reach consensus, that means that all the nodes in the network, they need to, I mean, when somebody proposes a node, all of them, in order to accept this consensus, they need to execute that node. They need to take the transactions and check the signatures, check that they have enough balance. If it's a VM machine, I mean, they need to execute the code or the smart contracts, the transactions. And if you want, and these nodes, if you want a really decentralized networks, these nodes cannot be huge nodes. I mean, well, you can put big nodes and you scale
to 5 machines.
Yeah, but I mean, if you want to, but this against decentralization. I mean, if you want to have relatively small nodes and you want to scale, this is limited. So the number of transactions that each node can execute is limited. So the cool thing here is that the zero knowledge allows you to, okay, maybe somebody gets transactions, somebody creates this zero knowledge, and then in the consensus layer, they don't need the nodes, they don't need to re-execute all these transactions. They just need to verify this proof and agree that this proof is valid. And this proof is, I tell you, it's very few milliseconds. Actually, you can do it in a smart contract in Ethereum, in NEAR. I think you also implement the pairings thing. So it's and so this is you can do that. And this is what really allows us to scale blockchains. Actually, there are two pieces. One is this execution, this technology, this ZK technology. And the other, of course, is the data availability. Data availability, okay, this is cool, but you need to put the data needs to be in the on-chain.
Well, to verify the proof, you need to see the data, whether the transactions went in, and you need everybody else to be able to actually reconstruct the state.
Exactly, so data needs to be available, because I could, I mean, the idea is, okay, I could reach a consensus for some valid state, but if you don't know how this state was built, nobody will be able to build the next state, because, okay, it's a hash root, okay, but you need
the information, yeah.
You need the information there. So an information requirements is that needs to be available, so that anybody should be able to have access to this information. This is the data availability. And I mean, looks like a simple program, a simple problem, but actually it's one of the hardest problems to solve. And by the way, I mean, NEAR is leading the space in this data availability. NEAR is one of the networks with best
sharded data
on the sharding with data availability. I mean, this is good in that side. So, yeah. So this is the
this is complementary to the kind
absolutely
of technologies. And I think kind of maybe to expand a little bit on this, the idea that any kind of computation anywhere can be proven with a succinct proof, right, and verified by anybody else within milliseconds. It also means that some of the things that right now, like you can only do with consensus, you can now kind of do in like, on the personal server, on some set of servers, and then just provide a proof. And so this kind of also unlocks a lot more provable compute, which is bringing us to the kind of broader vision, right, where people, are in control. And you like right now, if you're using any service, right, they can change their database. Like there's engineer who can like literally go and run an update query on your data, and you will not be able to like even detect that, right? But here you have this probability, and that's kind of fundamentally changing both the blockchain space, but also broader space. And so kind of bringing this to WebAssembly, so for us when we started, we actually banned the zero-knowledge words in our office, back when we had an office when we started. And this was from a reason that in 2019, it didn't really work. It didn't scale. It was really slow. It worked like on smaller things. Like back then, like it was hard to imagine EVM would be provable. And it would be too easy when we were designing NEAR to say, well, actually, this can be done with zero-knowledge proof, but we cannot implement it. And so, like, yes, there is a design with zero-knowledge proofs, but we cannot implement it. And so we ended up building the data availability, but also sharded execution and kind of the ecosystem around that. And people who've been at the talk yesterday for Bowen seen kind of the evolution of that. But with zero-knowledge now working, right, and especially kind of starting to scale to this more generic computation, being able to prove this zero-knowledge kind of for WebAssembly, and WebAssembly is a generic VM. It's VM that runs on every device. Like every device you have right now, there is a WebAssembly running on multiple different applications. It runs on edge, on IoT devices. It's a generic technology that has kind of very wide adoption. Being able to prove that will unlock kind of provable compute on edge. It will provide provable compute on your laptop, and it can provide provable compute for blockchains, and in turn also allow to continue scaling the blockchains and continue scaling the kind of what we can do with this technology.
Yeah, there is to mention maybe two important applications in the blockchain, because one thing is, of course, scaling blockchains themselves. I mean, building, call it a layer 2, but I mean, at the end is this set of data availability and the computational proof to scale. But this technology also plays an important role in trustless bridging. I mean, when you want to prove a chain in another chain, I mean, if the other chain are able to verify, you can prove the full chain, that the full state is in the other chain. So this is important for this trustless bridging. I like more the word, it's a little bit old, but this double pegging, just to distinguish the bridge of multi-sigs. I mean, this workaround. I mean, it's real bridging of blockchains. This is what allows you. This is trustless. I mean, you don't need to trust anybody. It's just the math, and then you can. I mean, you can prove one chain to another chain and one chain to another chain. So this allows us to connect different chain. So, I mean, connecting, for example, NEAR with Ethereum is perfectly possible with this technology.
And I think, I mean, that's an important note because indeed, right now, the bridges are either a multisig of some parties, or what we've had at NEAR and some other blockchains have is a light client verification, right? Where you just verify the block headers, but you don't verify that compute was correct. And so there is, an economic attack that's possible where if the value of the bridge is higher than, let's say, 30% or kind of, you can start actually doing some interesting things. Now, with zero knowledge, if you have a full client proof, right, the proof of all the computation, there's no way to actually violate the rules of the blockchain with whatever amount of stake. Like even if they have 100% of stake, they cannot actually violate it, right? And you need to change the circuit on the other side first to do that. And so that is kind of the benefit, but it also means that now the security of all the blockchains is getting kind of aligned. I call it kind of chain abstraction because you now have, the security of all the blockchains is getting more and more unified. And there's a lot of details how this is done, but now it's less about that and more about the applications and kind of things on top that people benefiting from.
Yeah, I mean, I think that having the WASM, ZK WASM, I mean, this should allow to prove the full near chain wherever. So this has a bunch of applications. Yeah. Another application that I think is important to mention is for light clients. Light clients, I mean, right now, if you have a mobile phone and you want to verify the chain, you either trust some server somewhere, or you can have you have the last block, and then you have a proof that the last block is the one that's correct. And this is, and you can't verify that block in a few milliseconds. Right now, a light client, they need to synchronize the full chain, or at least from a certain point. So this ZK WASM is also important. I mean, also for verifying the full chain in a mobile phone. So that's why I'm so excited on this for this technology. I think that this is for NEAR is a super important step for scaling, and we'll see that this will change the space. I mean, this technology will change the space of how the layer ones are. I mean, we were maybe in a place where there were like a lot of layer ones. Any application, any DApp or any application was thinking in creating their own layer one, and well, you know the difficulty that means creating layer ones. So I believe that's going to be a world where with much less layer ones and much more layer twos with these execution environments. And of course, WASM is an important piece for these layer twos.
Yeah, I think in general, it's the boundary between what is layer one and layer two is also kind of becoming less clear, right? Because
consensus. I mean, when we talk, at least in my mindset, when I hear layer one, I'm always thinking in the consensus layer. Probably, I think it's a better definition than layer one, because layer one is more. Yeah.
So there will be like
layer 0 and
layer 0. Yeah. So I think I agree that there will be more like. Even if there is more consensus layers, because you can prove each one. So like Ethereum as well, right? Polygon is working on type 1 prover, which allows to compress the whole Ethereum chain as well. So you will be able to do the same thing with Ethereum. And so you can put that Ethereum proof on NEAR. You can prove that Ethereum proof on Polygon POS, on Tender, on Cosmos
on different chains. I mean, in private chains, I mean, you can prove the full chain in another
exactly,
place.
And so similarly, you can run a private chain, or in our case, private shard, and prove that, and then like you don't need to reveal the data and transactions that happening there because, for example, it's a private shard, like for private transactions, but you can still verify to everyone that it's correctly executed, and it can hold balances, for example, on public chain for the users on private. So like there's new use cases that are kind of, because of this unification of security, that are opening up, as well as just generally kind of expanding what's possible with this, right? You can have a single server and have less censorship resistance. You can have a like separate consensus network and have censorship resistance. You can leverage other networks to kind of have forced transaction inclusion. So you can have all those different options. And indeed, like kind of this technology really opens this up, and we just seen kind of the beginning of this.
Exactly.
So I mean, and kind of within this topic, I think it might be interesting to talk about the value network and the kind of the aggregate liquidity and aggregate user base, right? Because I mentioned this that we're really trying kind of a lot of work in the ecosystem went into kind of making the experience easier, right? Making the interactions with blockchains more straightforward, easy for consumer. And at the same time, because of this kind of zero knowledge, full client proofs, aligning unification of security, what it means is now the value can smoothly move around, right? And so you guys kind of introduce this value layer nomenclature.
Exactly. The zero. I mean, the cool thing of these proofs is that once generated, I mean, you don't need to wait. It's already proven. Okay, this is compared, for example, with optimistic ways that, I mean, you need to wait for this challenging period and so on. So if we are able to create this proof fast enough, that means that the communication between the chains become fast. And if you have, and this is the idea of the Polygon 2.0, the idea of Polygon 2.0, the idea is to have like a different set of networks with different, maybe with different token, with different governance, some of them more centralized sequencer or other more decentralized sequencer, but they share single security rules. I mean, you do whatever you want, but the rules that manage the main bridge, or if you want the liquidity pool, you cannot do what you want. Okay, so you need to follow
you cannot like print tokens.
Exactly. So that's and here the rules are set in this ZK. And if you if you agree on these rules, on this ZK, then the idea is that the value transfers between the different chains can happen really, really fast. And this is the idea of the system. So that having different networks, but single liquidity, but then you can transfer the ownership through this zero knowledge, and this allows us to scale in a parallel way. Here we are talking always, the scalability goes in two directions. One thing is, scaling a single chain. This is zero knowledge is important, but then if you are able to connect the chains with fast transactions with this proof, then you have like, it's not having a processor that's fast, it's having like many processors. So you have many processors and those processors are fast. Here it's a new space. Here we open to a new era in the blockchain space.
Yeah, so Near actually was designed exactly like this, right? Just without zero knowledge. Lots of parallel processors, trying to interconnect them as fast as possible so you can actually move value between them, and then unifying the experience so users don't need to care about that. And so I think now with zero knowledge, working with Polygon, there's kind of an opportunity to broaden what that means, right? Not just for Near ecosystem, but also Polygon, Ethereum, and kind of even broader than that. And I think for, you always kind of, you obviously personally been in the Ethereum ecosystem very deeply. Polygon is obviously very close in this. I think I'm curious how you think about this kind of Ethereum alignment and kind of generally how do you think this evolving from the more lens of everybody working together?
Well, I think that this technology allows you to connect these networks. So I'm feeling that the isolation, maybe probably right now there is a lot of layer ones, and they are quite isolated one each other. And they have their own system, their own community is difficult to transfer. But these systems allows these connections, allow this. So here is, and at the end, we're sharing the same values, more or less.
Exactly.
All of us, we come from Bitcoin. So it's the idea of decentralization at some point. So I think that this technology is an opportunity to
work together.
Again. To work on that. Of course, each one comes from each network, his background, but joining and having a single internet, or having a single chain. If you want a set of chains that are constellation of chains that connects one each other, I think that this dream it's possible. thank you to this technology. We are very early in the stage. I mean, this technology is quite new. I mean, but I think this is clearly this is the way to go.
Yeah, it's like connecting. You know, we have right now South America internet, North America internet, European internet, and we're actually starting to connect them, and you've been able to
creating these highways. I mean, at the moment we have highways, so we have airlines that fly from one place to the other. So this, of course, will transform the world, or transform the world of blockchains. In this case.
So what are you most excited in the next year in kind of the space?
Well, I think that seeing these networks
working together,
connecting, seeing how it's scaling. For me, I mean, I'm in the space for the people to use it. As an engineer, for me, it makes no sense to build things that are useless. So my dream is to start seeing applications, start seeing many applications. I think that the possibilities are huge, and we have not started. I mean, the technology is not ready yet, at least for most of the applications that needs to come. So I hope that in the upcoming months and years, we'll start seeing this expansion and this, I mean, especially in the number of users and the users that take profit of this technology. That's what I'm more excited about.
Yeah, I agree. I mean, that's, you know, our focus has been on like how do we bring more consumer applications which can benefit from this technology, which can leverage it, and at the same time, you know, continue investing and innovating on the underlying layers such that there's more and more scale, but also, you know, versatility of the infrastructure and functionality. And so I think this partnership allows us to do a lot of cool things. It kind of allows to scale near blockchain itself. It allows to connect to other blockchains. It allows to also push things in more wider range of provable compute across kind of the whole, not just Web3, but broader technology space. And at the same time, it allows to kind of start to work together in a more, I would say, kind of friendly way, in such sense that we're actually not, you know, trying to build our own kind of small tribes, which always felt weird to me when we say, like, I mean, especially we frame everything as open web, and it's really weird when people are trying to close and like, okay, this is our ecosystem, right? It's like, well, it's kind of, we have a lot of, indeed, like shared value. We have a lot of things that we're working together on. We've been working with a lot of other blockchains from kind of early on, at least talking and making sure that the ideas are shared, the kind of the technology is, you know, moving along for everyone, and we are able to actually innovate here. And so, yeah, I'm really excited. I really appreciate you coming here, and I hope this was very informative and exciting. And we'll see a lot more of kind of innovation coming from this technology stack. Thank you.